Okay, so in this video, we are going to start talking about trigonometry. Trigonometry is essentially the study of triangles and the ratios of their sides and how their angles are related to their sides. So let's start off with a basic right triangle. Remember, we use this little box to denote a right triangle with a 90-degree angle. So let's label this to be A, B, and C with some angle x. Now, there's one familiar relation that we should go over first, and that's Pythagorean theorem, which, as you've probably seen before, says that a squared plus b squared is equal to c squared. So that it says this side length squared plus this side length squared gives you this one squared. And that's how you can calculate the different sides given two of the others. Okay, so let's start looking at this angle, because that might be the new thing. How does this angle relate to these sides? Well, why even study these? Well, here's the special thing about angles and sides. If you're given two triangles that have the same angles, we call these similar triangles, then the ratio of their sides will always be the same, no matter how big the triangles get. So if you were to take this length and divide it by that length, you can get the same thing as taking this length and dividing it by that length. So if we can figure out the ratio of these sides for this angle, no matter what size the triangle is, we can always use that ratio. So it's really helpful to define ratios of their sides. So we can start by doing that and say, well, let's define this side divided by this side. So we'll take B over C. We need to give it a name. So we're going to call it the sine of the angle. And if you were to write that out, you would spell this: sine of x. Okay? So the sine of an angle is the opposite side divided by the hypotenuse. Similarly, we can look at the ratio of this side to the hypotenuse. We say A over C. We'll call that the cosine of that angle. And if you were to write that out, it would be spelled cosine of x. Okay, so let's look at the last ratio we're going to look at today, and that is the opposite side over the adjacent side. So we have B over A. We call that the tangent of the angle. That's written tangent of x. Now, be careful with this word of. So just like when you were studying functions and you had f of x, this is the same thing. This is a function with an argument. It's not cosine times x. That doesn't make any sense. It's cosine with an argument of x. So you can think of this just as f of x, but this is a very special f of x. Okay, so let's calculate a couple of these. Let's see if we can figure out what the cosine and sine and tangent of some angle are. Okay, but before we do that, this may be a little hard to remember. So what we use is a very simple mnemonic that everybody's probably heard of before, and that is so. So, what does this mean? Sine is the opposite over hypotenuse. Cosine is the adjacent, or the side next to, divided by the hypotenuse. Tangent is the opposite over the adjacent. So, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. So if you can remember this mnemonic, you should have no trouble remembering which one is sine, which one is cosine, and which one is tangent. Okay, so let's do an example. So let's say we have the triangle, and it is a special triangle. We have a 45, 45, 90 triangle. Well, remember that if you have a 45, 45, 90, these two sides are the same. So we can label them as the same. We'll call this C still. So what we can do is say, well, the Pythagorean theorem says now a squared plus a squared is c squared, which means 2a squared equals c squared. So if we take the square root, we can get a square root of 2 equals c. We won't bother about the negative solution here because it doesn't make much sense to have a negative hypotenuse. So we can write c as a square root of 2. So now we can calculate all of our ratios in terms of our side length a. So we have sine of our angle, so we'll use this angle, is equal to the opposite over the hypotenuse. So the a's cancel, and you're left with 1 over the square root of 2. But remember, when you have 1 over a root, you need to rationalize it. And when you rationalize it, you get square root of 2 over 2. Let's look at cosine. So we have this length, which is a, divided by the hypotenuse. So you see you get the same thing. And now let's look at the tangent. So the tangent we have this length divided by that length. So we just have a over a. That's 1. So for any 45-degree angle, regardless of how big it is, it could be 5 miles long, it could be a millimeter long this way. It doesn't matter. For a 45-degree triangle, these are always true. The ratio of their sides will always be square root of 2 over 2, square root of 2 over 2, and 1. Okay, so let's look at another example. So let's say we now have the triangle looks like this. This is a 30-degree angle, and this is a 60-degree angle. Now, you've seen 30, 60, 90 triangles before, so we're just going to use the special lengths of their sides that you may have seen in your classes. So if this side length is 1, we know this side length is going to be square root of 3 over 2, and this side length is going to be a half. So we can use this to calculate the sine, cosine, and tangent of these angles. So let's do that. So let's start with the 30-degree angle. Sine of 30 degrees is going to be the opposite over the hypotenuse. Cosine of 30 degrees is going to be square root of 3 over 2 over 1, which is square root of 3 over 2. And the tangent is going to be 1/2 over square root of 3 over 2, which is 1/2 times 2 over square root of 3, which is 1 over the square root of 3. But we still need to rationalize it, so we get square root of 3 over 3. Okay, so that's the sine, cosine, and tangent of 30 degrees. What if we wanted to do 60 degrees? Well, let's do that. So, sine of 60, well, we now look at the opposite, which is opposite of this angle is this, divided by the hypotenuse. So we have square root of 3 over 2. Cosine of 60, well, that's going to be this side now, because this is adjacent to 60 over the hypotenuse. And the tangent is going to be the opposite over the adjacent. So square root of 3 over 2 divided by 1/2, which is the square root of 3 over 2 times 2, which is the square root of 3. Okay. so one more little shortcut to calculating tangent is, if you notice, it's just this number divided by that number. And that was the same thing for the other case too. So we can write that the tangent of x is really the sine of x over the cosine of x. Okay. So we've now developed a way to find sine and cosine for these special angles. But what if we wanted to do it for all triangles? Well, it gets a little more difficult because there's not always this very easy relationship to see. But what we can do is we can start to plot the values of these. So we now have the values of 30, 45, and 60. Let's get the values of sine and cosine of 0 and sine and cosine of 90 degrees, since those are kind of the two extremes. How are we going to do that? Well, let's look at the case where our triangle is extremely thin like this. So we have A, B, and C. We'll call this our angle X. Okay, well, as you can see, as B gets smaller and smaller, A and C approach the same length because they're collapsing in on each other. So we can say that the cosine of X, which is A over C, well, as B gets smaller and smaller, as the angle X goes to 0 and you don't have an angle, well, A is going to be C. So this is going to be 1. So we can say cosine of 0 is 1. So really this goes to 1 as that gets to 0. But the cosine of 0 is 1. Okay, well, remember sine of x is b over c, but as x goes to 0, b is getting smaller and smaller, and so b will be 0. So we say sine of 0 is 0. All right, let's look at the other extreme. Let's say that we have a triangle that the angle is getting very large this way. So let's say now this is our angle. This is our A, B, C. Okay, well, we now see that our A is getting smaller and smaller, and as x goes to 90, this will collapse in. So we have cosine of x equals A over C. So cosine of 90 will be 0 because A will go to 0 as it collapses in on itself. And the same argument can be made for sine of 90 that we made before, but this is going to go to 1 because B and C are going to approach to be the same line. Okay, so now we have these values. All right, so what's to be said about tangents of these values? Well, remember, the tangent is the sine over the cosine. So we get sine of 0 over cosine of 0. Well, sine of 0 is 0, cosine of 0 is 1. So that's 0 over 1, which is 0. So the tangent of 0 is 1, or 0. Let's look at this. So here we have the tangent of 90 degrees is the sine of 90 degrees over the cosine of 90 degrees. So what's that? Well, we're going to get 1 over 0. So that looks bad because you can't divide by 0. So for the tangent of 90, we say this does not exist. It blows up to infinity. So if you were to look at this, if you were to graph the tangent as it gets closer and closer to 90, it would just blow up to infinity. Because you're getting 1 divided by a smaller and smaller number, basically. Okay, so we now have a few points that we can deal with if we were to graph them. So let's try that. Let's try sine first. Let's get a nice coordinate system here. And let's plot some key values. 0, say 30, 45, and 60, and 90. All these are degrees. Okay. So sine of 0, 0. Sine of 30 is a half. Sine of 45 was the square root of 2 over 2. Sine of 60, square root of 3 over 2. Sine of 90 was 1. So there's not too much of a pattern emerging, but we can see it kind of curves off like this. So what happens if we start going beyond 90? Well, we see the same pattern start to appear. So if we were to extend this, so if our triangle goes from being like this to eventually being a 90-degree angle and then back around, what happens is the sine starts going back down because it's never going to be greater than it was here. So it starts to decrease, and it decreases in the exact same manner. So if we were to plot this even larger, we would see that the graph actually does something like that. And remember, sine of 0 is 0 because, well, the angle got smaller and smaller such that this side went away. Well, if we do the same thing over here, we see that this goes to 0 because this side goes away. So when your angle goes to 180 degrees, the same thing happens. So this is 0, and this is 180. Okay, so if we keep looking at this picture on a coordinate system, let's say our angle goes all the way down here. Let's say that this is our new angle. Well, this side now takes on a negative value. So we see that we get basically the same pattern as if we were to do it up here because these are the same lengths, except now we have negative. So we expect to get the same exact pattern just under the graph, basically. So this is, in fact, f of x equals sine of x. And here's the thing. We can keep going around this picture as much as we like. So what we can do is we can say this graph just extends and oscillates forever. Just like that. And it always has this constant spacing between, say, here and here. So the spacing between here and here is the same as the spacing between here and there, even if I didn't draw it that way. So whenever you see a graph that looks like this, this is sine of x, and it's very important that it start at 0. Now let's construct cosine in the same manner. So cosine of 0, recall, was 1. So cosine starts up here, and we know that cosine of 90 was 0. But it should also be true that cosine of 360, once you go all the way back around, is back up to 1. So we get something. Let me redraw that. We get something that basically looks like this. So it starts at 1, dips down, and goes back to 1. These should both. This should be a -1, and this should be a 1. So the graph of cosine, when you draw it all out, looks like this. It's exactly the same as the sine graph, except it's shifted. So if you were to take this and shift it by that much, you would in fact get sine of x. That's because sine and cosine are only off by what we call a phase. They're only off by this much of an angle. Now, it is important to note that both sine and cosine have their lower bounds at -1 and their upper bounds at 1. So it's always true that sine of x lies between these bounds and cosine of x also lies between these bounds. Okay, so that's nice for cosine of x. So we have cosine and we have sine. What about tangent? Because tangent had those really tricky 1 over zeros happening. Well, let's try to figure that one out. So let's start at the origin because we know tangent of 0 is 0. And then if you noticed, as our angles increased, the tangent started to increase. And it got bigger and bigger because it went to 1 over 0. So at 90 degrees, it blew up to infinity. So we can put an asymptote here. Now if we were to go the other way, the same negative angle argument we made before, or the same negative side length argument, the tangent will start to decrease. And it'll go to 1 over 0, but it'll be negative. So at minus 90, we have another one. But, just like before, we can keep going around the coordinate system and making bigger and bigger angles. And all that happens is this pattern repeats itself. And you just have an infinite number of asymptotes, depending how far you go. The same thing continues this way. So, as messy as it may seem, this is the graph of tangent of x. So, it's not nearly as nice as sine and cosine, but this is the graph of those two. So, when you're working with tangent of x, you have to be very careful not to include a point like 90 or negative 90 or 90. So, when you're looking at your domains, you have to look at this. Unlike sine and cosine, tangent is not bound between negative 1 and 1. Tangent is free to roam between negative infinity and infinity. So it is unbounded in its range, but it is bounded in its domain, unlike the other two. All right, so to wrap up this video, we're going to introduce 3 new trigonometric relations. So we had sine, cosine, and tangent, and all we're going to introduce is their reciprocals. So we define 1 over sine of x as the cosecant of x, which is written cosecant. We define 1 over the cosine of x to be secant of x. And we define 1 over the tangent to be the cotangent. So, if you ever want to find the cosecant, secant, or cotangent, just find the sine, cosine, or tangent and just take 1 over that value. It's simple as that.